What if I told you that the vast, glittering expanse of our universe, the galaxies, the stars, even the space between them, is being stretched apart by something we can't see, can't touch, and barely understand? Picture this: nearly 70% of everything that exists is made up of a force so elusive it defies detection. We call it dark energy, and it's not just some abstract idea. It's the invisible hand shaping the fate of the cosmos itself. Right now, as you watch this, the universe is expanding faster and faster, driven by this enigmatic power. But here's the real mystery: empty space, the void we once thought was nothing at all, might actually be crackling with energy, pushing the universe apart from within. This isn't science fiction, it's the cutting edge of physics. For decades, scientists have grappled with a question that sounds almost too strange to be real. Could the vacuum of space itself, that infinite stillness between stars, be the source of dark energy? Imagine the implications. The very nothingness we take for granted might hold the key to understanding why the universe isn't just growing, it's accelerating. And if that's true, it would mean that the laws of quantum mechanics, the rules governing the smallest particles in existence, are somehow intertwined with the grandest scales of the cosmos. It's a connection so profound, it could redefine our place in the universe. Today, we're going on a journey to the frontier of human knowledge, where the answers we find might challenge everything we thought we knew. We'll explore mind-bending theories, from the quantum fluctuations that constantly birth particles out of emptiness to the startling possibility that space itself is alive with energy. Along the way, we'll confront the puzzles that keep physicists awake at night. Why does dark energy behave the way it does? How can something so pervasive remain so hidden? And most tantalizing of all, what if the universe's greatest secret has been hiding in plain sight all along, woven into the fabric of the void? Strap in, because by the time we're done, you might never look at empty space the same way again. The discovery of dark energy in the late 1990s sent shockwaves through the scientific community, not because it fit neatly into our understanding of the universe, but because it shattered it. Picture astronomers peering into the depths of space, expecting to see the expansion of the cosmos slowing down under gravity's relentless pull, only to find the opposite. Distant supernova, those brilliant stellar explosions acting as cosmic mile markers, revealed something astonishing. The universe wasn't just expanding, it was accelerating, as if some unseen force was pressing its foot on the cosmic gas pedal. This wasn't just a small adjustment to the rules, it was a revolution. For centuries, we'd assumed gravity would eventually reign supreme, pulling galaxies back together in a big crunch. But dark energy flipped the script. Think of it like tossing a ball into the air, only to watch it shoot away faster instead of falling back down. The implications were staggering. If this mysterious force kept winning against gravity, the universe could face a far lonelier fate, an endless stretch into cold, empty darkness, where galaxies vanish over the horizon of space itself. So what is dark energy? Here's where things get even stranger. The leading theory suggests it might be an intrinsic property of space itself, a sort of energy woven into the vacuum, often called vacuum energy. According to quantum mechanics, empty space isn't truly empty. It's a seething ocean of virtual particles popping in and out of existence, giving the void a faint, thrumming energy. If this energy permeates all of space, it could explain the repulsive force driving cosmic acceleration. But there's a catch. When physicists crunch the numbers, the predicted energy of the vacuum is laughably off by a factor of 1 followed by 120 zeros. That's not just a rounding error, It's the biggest mismatch between theory and observation in all of science. This leaves us with two haunting possibilities. Either we're missing something fundamental about how quantum energy works, or dark energy is something entirely different, perhaps a new kind of field or force that changes over time. Some theories even suggest it could be tied to extra dimensions or hidden aspects of reality we haven't yet imagined. Every answer seems to lead to deeper questions, and that's what makes this mystery so exhilarating. Dark energy isn't just a puzzle for astronomers, it's a challenge to the very foundations of physics, daring us to rethink what we know about space, time, and the nature of existence itself. One thing's certain, the more we learn, the more the universe surprises us. And that's the beauty of science. It's not about having all the answers, but about asking the right questions, even when they lead us to the edge of the unknown. Let's zoom in on the quantum realm, where the rules of the everyday world break down and reality becomes a swirling dance of probabilities. Even in what we call empty space, there's a hidden frenzy of activity, virtual particles flickering into existence for unimaginably short moments before vanishing again. This isn't just theoretical speculation. It's a well-tested prediction of quantum field theory, confirmed by experiments like the Casimir effect, where two metal plates placed incredibly close together feel a subtle push from these quantum fluctuations. Think of the vacuum like a bubbling pot of water, where particles and their antimatter counterparts, electrons and positrons, quarks and antiquarks, constantly emerge and annihilate in a blink. This seething quantum foam isn't just empty nothingness. It crackles with energy, a kind of baseline hum to the universe. And here's where things get mind-bending. If this energy permeates all of space, it could act like a cosmic repellent, pushing galaxies apart and accelerating the expansion of the universe. In other words, vacuum energy might be dark energy, but there's a colossal problem. When physicists calculate how much energy these quantum fluctuations should contribute, the number is staggeringly large, enough to rip the universe apart instantly. Yet observations show dark energy's effect is far, far weaker, like comparing the force of a hurricane to a gentle breeze. This mismatch isn't just puzzling. It's one of the most glaring discrepancies in modern physics, suggesting we're missing something profound about how quantum mechanics and gravity interact. Some theorists argue that maybe these quantum effects cancel out in ways we don't yet understand, leaving behind just a faint residue, the dark energy we detect. Others propose that our understanding of gravity itself might need revising, or that entirely new physics is at play. One thing's clear, the quantum vacuum isn't just background noise. It's an active player in the cosmos, and unlocking its secrets could rewrite the story of the universe's fate. The deeper we dig, the more we realize that nothing might be the most something of all. Einstein's cosmological constant is one of history's most fascinating twists, an idea born from a mistake that might hold the key to the universe's greatest mystery. Back in 1917, when Einstein was crafting his theory of general relativity, most scientists believed the cosmos was static, unchanging, but his equations kept predicting a universe that either expanded or collapsed under gravity's pull. To force the math into alignment with the prevailing view, he tacked on an extra term, a repulsive force he called the cosmological constant, to keep everything perfectly balanced. It was a clever fix, but when Edwin Hubble later discovered the universe was expanding, Einstein famously dismissed his own addition as his greatest blunder. Yet here's the irony. Decades later, the discovery of dark energy resurrected the cosmological constant from scientific exile. Turns out, Einstein might have been right for the wrong reasons. If the constant represents the energy of empty space, a kind of inherent push woven into the fabric of reality, it could perfectly explain why the universe's expansion is accelerating. The math even fits. A cosmological constant with just the right strength would produce exactly the effects we observe. But there's a catch that keeps physicists up at night. When we try to calculate this energy using quantum mechanics, the numbers explode into absurdity. The predicted vacuum energy is 10 to the power of 120 times larger than what we actually measure. That's like expecting a whisper and getting a supernova instead. This staggering mismatch is the heart of the cosmological constant problem, and it hints at something profound. Either our understanding of quantum physics is incomplete, or gravity behaves in ways we haven't yet imagined. Some theorists suggest that unknown symmetries in nature might cancel out most of the vacuum's energy, leaving behind just a faint trace, the dark energy we detect. Others propose that the constant isn't really constant at all, but a dynamic field that evolves over time, like an invisible river shaping the cosmos. Then there's the radical idea that our universe is just one bubble in a vast multiverse, where the value of the cosmological constant is a random roll of the dice, and we just happen to live in a pocket where the number is bizarrely small. What makes this puzzle so thrilling is that it forces us to confront the limits of our knowledge. Einstein's blunder might have been a stroke of accidental genius, a placeholder for a deeper truth we're still unraveling. Whether the cosmological constant is the final answer or just a clue leading us toward something even stranger, one thing's certain: the universe loves a good plot twist. And as we piece together the story of dark energy, we're not just solving equations, we're rewriting the very definition of nothingness. At the heart of the dark energy mystery lies a cosmic tug of war between two titans of physics: quantum field theory and general relativity. Each brilliantly explains its own domain. Quantum field theory governs the chaotic, probabilistic world of particles, while general relativity paints space-time as a smooth, curving stage where gravity plays out. But when these theories try to explain the same phenomenon, like the energy of empty space, their predictions couldn't be more different. It's as if two master artists painted the same landscape, one with wild, vibrant splashes and the other with serene, precise strokes, leaving us staring at two entirely different visions of reality. Quantum field theory tells us the vacuum should be brimming with energy. Every cubic centimeter of space, no matter how empty it seems, is a storm of virtual particles flickering in and out of existence. Add up all that activity across the universe, and the energy density should be colossal enough to warp space-time beyond recognition. Yet when we turn to general relativity, the equations suggest dark energy's effect is incredibly subtle, a faint whisper nudging galaxies apart. The mismatch isn't just slight, it's like comparing the energy of a lit match to the output of 1,000 suns. How can two such successful theories be so wildly at odds? Some physicists believe the answer lies in the gaps between these frameworks. Quantum field theory excels at describing the very small, while general relativity rules the cosmic scale. But dark energy sits at their intersection, forcing us to ask, does one theory need tweaking, or is there a grander theory waiting to be discovered, one that unifies them both? Candidates like string theory or loop quantum gravity attempt to bridge this divide, but so far, none have delivered a definitive solution. Others propose a radical idea. What if dark energy isn't a static force but something that evolves, weakening over time? That could mean the accelerating expansion we see today is just a phase, a fleeting moment in the universe's long story. Then there's the possibility that we're simply missing a hidden layer of physics. Imagine trying to understand a symphony by listening to just the violins or the drums. You'd miss the harmony. Similarly, dark energy might emerge from interactions we haven't yet imagined, a cosmic rhythm only audible when both quantum and gravitational instruments play together. Whatever the answer, this clash isn't just academic, it's a doorway. Solving it wouldn't just explain dark energy, it could reveal how the universe truly works, from the smallest quantum flutter to the vast, stretching cosmos. And that's the kind of discovery that doesn't just rewrite textbooks, it changes how we see reality itself. Even in the deepest cold of absolute zero, where classical physics says all motion should cease, the quantum world refuses to sit still. This restless energy, this eternal hum of particles jittering in place, is what physicists call zero-point energy. It's the baseline vibration of reality itself, proof that true emptiness doesn't exist. And here's where things get wild. If we could somehow tap into this energy, even a single cubic centimeter of empty space would contain enough to boil all the oceans on Earth. That's the staggering power hidden in what we mistakenly call nothing. Now, here's the cosmic puzzle. If zero-point energy floods every corner of the universe, could it be the engine behind dark energy? At first glance, the idea makes perfect sense. Both are properties of the vacuum. Both exert influence at unimaginable scales. But when scientists crunch the numbers, the math spirals into absurdity. The predicted energy density of the quantum vacuum overshoots dark energy's observed effect by a factor of 1 followed by 120 zeros. To put that in perspective, it's like calculating the weight of a feather and getting an answer heavier than the entire observable universe. So what's going wrong? One possibility is that we're missing a crucial piece of the puzzle, some undiscovered symmetry or cancellation mechanism that tames zero-point energy's ferocious predictions. Think of it like a perfectly tuned orchestra where instruments playing in opposite directions create harmony instead of noise. Maybe the universe has a built-in way to balance these quantum fluctuations, leaving behind only a faint echo, the gentle push we call dark energy. Others argue the discrepancy hints at something deeper, that zero-point energy and dark energy might be entirely separate phenomena. Imagine two hidden rivers flowing through space, one a raging torrent, the other a slow, steady current. Both shape the landscape, but only one is responsible for the cosmic acceleration we observe. This wouldn't just solve the energy mismatch. It would mean the vacuum is even stranger than we thought, with layers of activity we've yet to untangle. Then there's the radical notion that zero-point energy doesn't gravitate the way we expect. General relativity assumes all energy curves space-time, but what if quantum vacuum energy plays by different rules? Some theories suggest it might cancel out gravitationally, like a cosmic sleight of hand where the left hand undoes what the right hand creates. If true, it would mean our understanding of gravity is incomplete, a realization that could rewrite physics from the ground up. Whatever the answer, zero-point energy forces us to confront a humbling truth. The universe resists simple explanations. It's as if we've been handed a key that almost fits the lock, teasing us with glimpses of a door we can't yet open. But that's the thrill of the hunt. Every miscalculation, every mismatch is a clue pointing toward something deeper, a reminder that the cosmos still holds mysteries waiting to shake the foundations of what we know. And somewhere in the quantum whisper of empty space, the next great revelation might already be vibrating just beyond our reach. The Casimir effect is like a ghostly handshake between the quantum world and our own, a phenomenon so subtle, yet so profound, it gives us our first tangible glimpse of vacuum energy in action. Picture two ultra-thin metal plates placed unimaginably close together in a perfect vacuum, just a few nanometers apart. Classical physics would say nothing should happen. After all, there's no charge, no magnetism, no obvious force at play. But in reality, the plates are irresistibly drawn together, as if space itself is pushing them. This isn't magic, it's quantum mechanics revealing its hidden layers. What's really happening between those plates, only certain wavelengths of quantum fluctuations can fit, like waves in a bathtub that must bounce back perfectly between the walls. But outside the plates, an infinite spectrum of fluctuations thrums undisturbed. The imbalance creates a pressure differential, a literal force emerging from nothingness, pushing the plates together. It's as if the universe is whispering, empty space is never truly empty. The Casimir effect proves that the quantum vacuum isn't just a theoretical idea. It's a dynamic, energetic medium with measurable consequences. Now here's the leap that ties this to dark energy. If the vacuum can exert force on microscopic scales, could a similar mechanism on a cosmic scale be driving galaxies apart? At first glance, the parallel seems compelling. Both phenomena stem from quantum fluctuations. Both involve energy inherent to space itself, but the devil's in the details. The Casimir effect is an attractive force while dark energy repels. More critically, the energy density behind the Casimir effect is enormous compared to the faint, smooth push of dark energy. Scaling up from lab-sized plates to the vastness of the cosmos introduces staggering theoretical hurdles. One major challenge is the cutoff problem. In calculations, the Casimir force depends on summing up all possible quantum fluctuations, but infinities creep in unless we impose an arbitrary limit, like ignoring fluctuations smaller than a Planck length. On cosmological scales, this cutoff becomes a philosophical quagmire. Why would nature choose one scale over another, and even if we fudge the math, the numbers still don't align? The vacuum energy we measure in the lab is orders of magnitude stronger than the gentle nudge of dark energy. It's like comparing the roar of a jet engine to the rustle of a single leaf. Both are sounds, but they belong to entirely different worlds. Yet the Casimir effect remains a crucial clue. It tells us that vacuum energy is real, measurable, and capable of influencing the physical world. The disconnect with dark energy might not mean the idea is wrong, just incomplete. Perhaps there's a cancellation mechanism we haven't discovered, or maybe dark energy arises from a subtler aspect of vacuum behavior, like fluctuations in a hidden field. Some theorists even speculate that the Casimir effect, in extreme conditions like near black holes or in the early universe, could manifest repulsive properties we haven't yet observed. What makes this so thrilling is that we're not just grappling with equations, we're probing the fabric of reality. Every time we observe the Casimir effect, we're witnessing quantum mechanics flexing its muscles, reminding us that nothing is a canvas teeming with activity. And if we can bridge the gap between these tiny lab curiosities and the grand sweep of cosmic expansion, we might finally crack one of the universe's greatest mysteries. Until then, the Casimir effect stands as both a triumph and a tantalizing hint, a signpost pointing toward truth still just beyond our grasp. String theory dangles a tantalizing possibility. What if dark energy isn't just hidden in the fabric of space, but woven into dimensions we can't even see? Imagine the universe as a vast, multidimensional tapestry with our familiar 4 dimensions: length, width, height, and time, just the visible threads. Beneath the surface, tiny, curled-up dimensions could hold the missing pieces of the puzzle, vibrating with energy that leaks into our reality as the force we call dark energy. It's a radical idea, but one that could bridge the gap between quantum mechanics and gravity, unifying the laws of the very small and the cosmic. At the heart of string theory lies the concept of brains's membranes floating in higher dimensional space, some stretched across vast distances, others compacted into scales smaller than an atom. Our entire universe might exist on one such brane, with dark energy arising from the tension between branes or the subtle curvature of these hidden dimensions. Picture it like a ripple on the surface of a pond. What we perceive as dark energy could be the gravitational echo of something happening in a dimension we'll never see directly. Some models even suggest that dark energy isn't constant, but tied to the slow evolution of these extra dimensions, like invisible gears turning behind the scenes of reality. Then there are the scalar fields, invisible, omnipresent forces that string theory predicts could permeate the cosmos. Think of them like an ethereal wind blowing through space, gently pushing galaxies apart. One such field, the quintessence field, might interact with matter in ways that mimic the cosmological constant, but with a twist. Its strength could change over time. Unlike the static vacuum energy of traditional models, quintessence offers a dynamic explanation for dark energy, one that could explain why its effects seem finely tuned, almost as if the universe calibrated itself to allow life to exist. But here's the catch: string theory's beauty is also its biggest hurdle. Without experimental proof, its ideas remain dazzling speculation. The energy scales required to probe extra dimensions or detect strings are far beyond our current technology, like trying to hear a whisper from across a hurricane. Even the Large Hadron Collider, the most powerful particle accelerator ever built, can't directly test these predictions. Critics argue that string theory has become a playground of mathematical elegance untethered from reality, while proponents counter that some truths are simply too profound to reach easily. Yet, even if string theory's connection to dark energy remains unproven, it offers something invaluable: a roadmap. By daring to imagine higher dimensions, vibrating strings, and hidden fields, physicists are stretching the boundaries of what's possible. Every dead end, every mathematical inconsistency forces us to refine our questions. Maybe dark energy isn't just a mystery to solve, but a signpost pointing toward a deeper layer of reality, one where the fabric of space isn't just stretched, but intricately folded, vibrating with secrets we've only begun to sense. And that's the essence of science, not just finding answers, but learning how much more there is to ask. What if dark energy isn't a fixed feature of the universe, but something alive, shifting, evolving, even fading over time? This is the bold idea behind quintessence, a theory that challenges the notion of vacuum energy as the sole culprit behind cosmic acceleration. Picture a cosmic chameleon, a field that permeates all of space but changes its strength depending on when and where you look. Unlike the static cosmological constant, quintessence behaves more like a fifth fundamental force, one that might hold the key to some of the universe's most perplexing mysteries. The name itself is a nod to ancient philosophy. Aristotle's quintessence was the elusive fifth element beyond earth, air, fire, and water, thought to fill the heavens. Today, physicists have repurposed the term for a dynamic field that could explain why dark energy's effects seem so finely tuned. Here's how it works. While vacuum energy is like a relentless, unchanging push, quintessence ebbs and flows, its repulsive strength waxing or waning over billions of years. This flexibility could solve a nagging problem in cosmology, the coincidence problem. Why is dark energy's density roughly the same as matter's right now, after eons of expansion? If dark energy were truly constant, this balance would be astronomically unlikely, like two strangers randomly meeting in a vast desert. But if quintessence evolves, it might naturally sync with matter's density at certain epochs, making our current era less of a fluke. Some models suggest quintessence could have played a role in the universe's infancy, driving inflation, that explosive early expansion, before fading into obscurity, only to re-emerge recently as dark energy. Others propose it interacts with dark matter, creating a cosmic dance where the two invisible giants influence each other in ways we're only beginning to model. The most tantalizing possibility, Quintessence might not just explain the universe's acceleration, it could predict its future. If the field continues weakening, dark energy's grip might loosen, allowing gravity to regain dominance. Alternatively, if it grows stronger, the universe could face a big rip, where even atoms are torn apart by runaway expansion. Of course, Quintessence isn't without its critics. For one, it introduces new unknowns. What triggers its changes? What laws govern its behavior? And why haven't we detected its fluctuations directly? Unlike the cosmological constant, which is simple but stubbornly mismatched with quantum predictions, Quintessence trades one mystery for many. Yet that's also its strength. By embracing complexity, it opens doors to explanations a static vacuum never could. Whether Quintessence is real or just a clever workaround, it reminds us that the universe rarely fits into neat boxes. Sometimes, the most compelling answers lie not in what we can see, but in what might still be moving quietly, invisibly, beneath the surface of reality. The story of dark energy's discovery reads like a cosmic detective novel with clues scattered across the night sky. The first breakthrough came from something seemingly catastrophic, the explosive deaths of stars. Type 1, a supernova, often called standard candles, burn with such consistent brightness that astronomers can use them to measure cosmic distances with remarkable precision. In the late 1990s, two independent teams were studying these stellar explosions, expecting to confirm that the universe's expansion was slowing under gravity's pull. Instead, they found the opposite. The most distant supernovae were dimmer than expected, meaning they were farther away than anyone had predicted. The universe wasn't just expanding, it was accelerating, as if some invisible force was giving it an extra push. That shocking revelation earned the researchers the Nobel Prize and forced science to confront the reality of dark energy. But supernovae weren't the only evidence. The cosmic microwave background radiation, the faint afterglow of the Big Bang itself, holds fingerprints of dark energy's influence. When the European Space Agency's Planck satellite mapped this relic radiation in exquisite detail, it revealed subtle patterns in the universe's early structure. Patterns that only make sense if dark energy makes up about 68% of the cosmos. Think of it like finding an unexpected ingredient in a recipe. The proportions were all wrong without dark energy's presence. Then there's the large-scale structure of the universe, the vast web of galaxies stretching across billions of light years. Surveys like the Sloan Digital Sky Survey have shown how dark energy subtly warps this web, pushing galaxies apart faster than gravity can pull them together. Yet for all these observations, dark energy remains maddeningly indirect. We see its effects the way it bends light, the way it stretches space, but we've never caught it in the act. That's where the next generation of telescopes comes in. Instruments like the Vera-C, Rubin Observatory, and NASA's Nancy Grace Roman Space Telescope will map billions of galaxies, hunting for tiny distortions in their shapes caused by dark energy's push. Others, like the Dark Energy Spectroscopic Instrument, will create three-dimensional maps of the cosmos, tracking how galaxy clusters move over time. These projects aren't just about collecting data, they're about ruling out possibilities. Is dark energy truly constant, or does it vary across space and time? Does it interact with dark matter, or is it entirely separate? And then there's the wild card gravitational waves. When black holes collide, they send ripples through space-time itself. By studying these waves, scientists hope to measure the universe's expansion rate independently, offering a fresh test for dark energy theories. It's like listening to the universe's heartbeat, searching for irregularities that might reveal its hidden driver. Every observation, every experiment is a piece of the puzzle, and with each new discovery, we get closer to answering the ultimate question: what is dark energy, really? The universe is giving us hints. We just have to learn how to listen. Right now, cosmology is facing a crisis not of confidence, but of numbers. Two of the most trusted ways to measure how fast the universe is expanding are giving us different answers, and the gap between them is widening like the cosmos itself. It's called the Hubble Tension, and it's more than just a technical hiccup. It could be the first crack in our understanding of dark energy and the fate of everything. On one side, we have the cosmic microwave background, the afterglow of the Big Bang. By studying its subtle fluctuations with satellites like Planck, scientists can extrapolate the universe's expansion rate, what's known as the Hubble constant. This method paints a picture of a cosmos expanding at about 67 kilometers per second per megaparsec, a speed that's held steady for billions of years. But then there's the other approach, measuring the distances to nearby supernova and pulsating stars called Cepheids. These observations suggest a faster expansion, around 73 kilometers per second per megaparsec. At first glance, the difference seems small, but statistically, it's like two clocks ticking at irreconcilable rhythms, one calibrated to the dawn of time, the other set by the stars in our cosmic backyard. So what's going on? One possibility is that dark energy isn't the constant force we've assumed. Imagine blowing up a balloon in slow motion, then suddenly giving it an extra puff. If dark energy's strength has increased over time, it could explain why local measurements show a speedier expansion than ancient light predicts. Alternatively, there might be unknown particles, sterile neutrinos or other exotic relics, altering the early universe's density in ways we haven't accounted for. Some theorists even speculate that dark energy interacts with dark matter, creating a feedback loop that's subtly warping the expansion rate. Then there's the radical idea that our corner of the universe isn't entirely representative. Picture a vast ocean where most of the water is calm, but you're floating in an unusually turbulent eddy. If we're sitting in a local underdensity, a cosmic void where matter is sparser than average, gravity's weaker grip here might make expansion appear faster than it truly is globally. It's a long shot, but if true, it would mean our entire cosmic neighborhood is an outlier, skewing our perception of reality. The stakes couldn't be higher. If the Hubble tension persists, it could mean our standard model of cosmology, the meticulously constructed framework that explains everything from the Big Bang to dark energy, is missing a crucial piece. Perhaps gravity behaves differently on vast scales, or the universe underwent a phase transition we haven't yet imagined. Every new observation, from gravitational wave detectors to next-generation telescopes, is a chance to test these wild hypotheses. And that's the beauty of science. When the numbers don't add up, it's not a failure, it's an invitation to dig deeper, to question assumptions, and maybe, just maybe, stumble upon a truth even stranger than we've dared to dream. The fate of the universe hinges on a delicate cosmic balancing act, one where dark energy plays the lead role in a drama spanning trillions of years. Picture this. If dark energy's repulsive force continues unchallenged, the universe won't just expand, it'll escalate into a runaway acceleration so extreme it could shred reality itself. Scientists call this nightmare scenario the Big Rip. Here's how it unfolds. First, galaxy clusters would be torn apart, their gravitational bonds no match for dark energy's mounting strength. Next, individual galaxies would unravel, stars flung into the void like sparks from a fire. Then, as space stretches faster than the speed of light itself, solar systems would disintegrate, planets ripped from their orbits. In the final, chilling moments, even atoms would be torn asunder, their nuclei unable to withstand the cosmic tension. The universe would end not with a bang, but with a silent, infinite scream, a void where not even particles remain. But there's an alternative one where dark energy loses its grip. Imagine a universe where this mysterious force weakens over time like a fading echo. Gravity, the patient architect of cosmic structure, could gradually reassert itself. Galaxies would slow their flight, then reverse course, drawn back together in a celestial homecoming. Over eons, matter would condense, temperatures would rise, and the universe might collapse in a fiery, big crunch, a mirror image of the Big Bang, where everything that ever was compresses into a singularity. Some theories even suggest such a collapse could birth a new universe, cycling back into another explosion of space and time. Then there's the middle path, a universe where dark energies push and gravities pull reach an uneasy stalemate. Expansion would continue, but ever more slowly, like a car coasting on empty. Galaxies would redshift into darkness, stars would burn out, and the cosmos would settle into a frigid, eternal twilight, the so-called heat death. In this scenario, the universe doesn't tear apart or collapse. It simply exhausts itself, all energy diffused, all structure dissolved into a featureless equilibrium. What makes these possibilities so haunting is that they're not just speculative fiction, they're grounded in real physics. The equations of general relativity allow for all three outcomes, and the deciding factor is dark energy's true nature. Is it a constant force, as Einstein's cosmological constant suggests, or is it dynamic like Quintessence, capable of strengthening or fading over time? Even tiny differences in its properties could steer the cosmos toward radically different futures. This isn't just about satisfying curiosity. Understanding dark energy is like reading the universe's last will and testament, a clue to whether everything we see, from the tiniest atom to the grandest galaxy, is destined for oblivion, rebirth, or something stranger still. And while these timelines stretch far beyond human comprehension, they remind us that the cosmos is anything but static. It's a living, evolving entity, and dark energy is the unseen hand guiding its ultimate fate. The question isn't just academic, it's existential, because in deciphering dark energy, we're not just mapping the universe's end, we're discovering what it means, in the deepest sense, to be part of its story. The vacuum catastrophe is perhaps the most baffling discrepancy in all of physics. A miscalculation so vast, it would be laughable if it weren't so profound. According to quantum field theory, empty space should be a roaring tempest of energy, with virtual particles bursting in and out of existence at every moment. Add up all that activity, and the vacuum's energy density should be around 1 followed by 112 zeros joules per cubic meter. That's an unimaginably large number, enough to warp spacetime into knots instantly. Yet when we measure dark energy's actual effect on cosmic expansion, it's almost vanishingly small, about 1 followed by just 9 zeros. The difference between prediction and observation isn't a minor rounding error. It's like expecting the force of a supernova and feeling the brush of a single photon instead. This staggering mismatch forces physicists to confront two unsettling possibilities. Either our understanding of quantum fields is fundamentally incomplete, or there's a hidden mechanism in nature that cancels out nearly all this vacuum energy, leaving behind just the faintest whisper, the dark energy we observe. One proposed solution comes from supersymmetry, an elegant but unproven theory that posits every known particle has a heavier superpartner. If supersymmetry were perfectly balanced, the contributions of particles and their superpartners to vacuum energy could cancel out, like perfect mirror images negating each other. The catch: we've found no evidence of these superpartners in particle colliders, and even if they exist, supersymmetry would need to be broken in just the right way to leave behind dark energy's subtle signature. Another idea takes inspiration from the holographic principle, which suggests the information in a volume of space might actually be encoded on its surface. If true, the vacuum's energy could be smeared across this boundary, drastically reducing its observable impact. Then there's the radical notion that gravity itself behaves differently at quantum scales, perhaps weakening the influence of vacuum fluctuations in ways we haven't yet modeled. Some theorists even speculate that our universe is one bubble in a vast multiverse, where most bubbles have vacuum energies too extreme to support life, making our oddly tiny dark energy a cosmic fluke, a statistical outlier in an otherwise inhospitable landscape. What makes this puzzle so thrilling is that it's not just a numbers game. The vacuum catastrophe is a direct challenge to how we reconcile quantum mechanics with gravity, two pillars of physics that refuse to play nicely. Every proposed solution forces us to rethink reality at the deepest level. Maybe the vacuum isn't what we thought. Perhaps empty space hides dimensions, fields, or symmetries we've yet to uncover. Or maybe dark energy isn't vacuum energy at all, but something entirely different, masquerading as a cosmological constant. Until we crack this riddle, the vacuum catastrophe stands as both a humbling reminder of how much we don't know and an irresistible beacon drawing us toward the next great breakthrough. Because in the end, the universe's greatest mysteries aren't just problems to solve. They're invitations to dream bigger. Quantum gravity is the holy grail of modern physics, the missing piece that could finally unite the bizarre, probabilistic world of quantum mechanics with the smooth, curving cosmos of general relativity. Right now, these two frameworks speak entirely different languages. Quantum mechanics thrives on uncertainty, where particles pop in and out of existence, and reality is a game of probabilities. Gravity, on the other hand, paints spacetime as a serene stage, warped by matter in precise, predictable ways. But when we try to merge them, the math explodes into nonsense. And dark energy might just be the Rosetta Stone we've been searching for, a cosmic clue written in the accelerating expansion of the universe itself. Take loop quantum gravity, one of the boldest attempts to crack this puzzle. Instead of imagining space as a blank canvas, this theory proposes it's woven from tiny, indivisible loops. Think of it as a cosmic tapestry where each thread is a billion times smaller than an atom. These loops vibrate and interact, creating the fabric of spacetime itself. Here's where it gets wild. If these loops have a natural, repulsive property at extreme densities, they could mimic dark energy's effects, driving cosmic acceleration without invoking mysterious fields or vacuum energy. It's like discovering that the stitches in a quilt have been pushing it apart all along. Then there's emergent gravity, a radical idea that turns our understanding of gravity upside down. What if gravity isn't a fundamental force at all, but an illusion, a side effect of deeper, hidden processes? Imagine a crowd of people moving in a stadium. From a distance, their collective motion might look like a wave, even though no single person is the wave. Similarly, emergent gravity suggests that what we perceive as gravity emerges from the way information is structured on the tiniest scales of spacetime. In this view, dark energy could be a shadow of that underlying structure, a cosmic mirage revealing the gaps in our current theories. String theory offers yet another angle, with its vibrating strands of energy dancing in hidden dimensions. Some string models suggest dark energy arises from the way these strings interact with higher dimensional branes, like ripples on the surface of a pond. Others propose that the vacuum energy predicted by quantum fields is partially cancelled out by these extra dimensions, leaving behind just the faint residue we observe as dark energy. But here's the catch: string theory is notoriously hard to test, and without experimental proof, it remains a dazzling but unconfirmed vision of reality. The stakes couldn't be higher. If any of these theories succeed, they wouldn't just explain dark energy, they'd rewrite the rules of the universe. Picture a world where space-time is granular, where gravity is an illusion, or where hidden dimensions tug at reality from behind the scenes. Each possibility is more mind-bending than the last, but that's the thrill of the hunt. Dark energy isn't just a mystery to solve. It's a doorway, inviting us to step beyond the limits of known physics and into a deeper understanding of how everything from the tiniest particle to the vast, stretching cosmos fits together. And that's the kind of discovery that doesn't just answer questions, it changes them. Scientists are turning the cosmos into a laboratory, deploying everything from tabletop quantum experiments to billion-dollar space telescopes in the hunt for dark energy's elusive signature. On Earth, labs are probing the quantum vacuum with unprecedented precision, using devices like atomic interferometers to measure minuscule forces that might reveal dark energy's influence at microscopic scales. Imagine suspending atoms in a vacuum with lasers, watching how they subtly jitter under the unseen push of quantum fluctuations, a dance that could hold clues to how vacuum energy manifests on cosmic scales. These experiments are like tuning forks for spacetime, sensitive enough to detect whispers of the universe's hidden engine. Meanwhile, in the depths of space, a new generation of observatories is taking aim at dark energy's grand effects. The European Space Agency's Euclid telescope, launched in 2023, is mapping the distribution of galaxies and dark matter across 10 billion light-years, tracing how dark energy has sculpted the universe's large-scale structure over eons. Its measurements are so precise, they could detect variations in dark energy's strength down to 1%, a level of accuracy that might finally settle whether it's truly a constant or something more dynamic. Then there's NASA's upcoming Nancy Grace Roman Space Telescope, set to launch later this decade. With a field of view 100 times wider than Hubble's, Roman will conduct a sweeping survey of the cosmos, measuring the shapes and distances of millions of galaxies to track how dark energy's push has evolved across cosmic time. But the real game changer might come from combining these approaches. By cross-referencing lab data with astronomical observations, physicists hope to bridge the gap between quantum mechanics and cosmology. For instance, if lab experiments confirm unexpected behavior in vacuum energy, while telescopes find corresponding anomalies in cosmic expansion, it could signal a deeper connection between the tiny and the vast. Alternatively, discrepancies might point toward entirely new physics, like extra dimensions or modified gravity. The stakes are sky high. Dark energy's equation of state, whether it's a steadfast constant or a shifting force, will determine not just the fate of the universe, but which of our theories survive. A changing value could support quintessence models, while a perfect constant would bolster Einstein's cosmological constant, however puzzling its quantum mismatch remains. And if the data defies all predictions, that's when things get truly exciting, because the greatest discoveries often lie in the places our theories fail. Every measurement from the lab bench to the edge of the observable universe brings us closer to answering the question that haunts modern physics. What exactly is dark energy, and why does it hide in plain sight? Black holes, those cosmic vacuum cleaners where gravity is so strong not even light can escape, might have a surprising relationship with dark energy, one that could rewrite our understanding of both. Picture a supermassive black hole at the center of a galaxy, its immense pull devouring stars and gas. Now imagine dark energy, that invisible force stretching space itself, subtly tugging back. According to recent theories, these two titans might be locked in a quiet but profound cosmic duel, with dark energy potentially slowing black hole growth over astronomical timescales. It's like a tree growing in a hurricane. No matter how strong its roots, the relentless wind shapes its ultimate size. But the interplay gets even stranger when we consider Hawking radiation, the faint glow of particles predicted to leak from black holes due to quantum effects near their event horizons. Here's the twist: if dark energy is indeed the energy of empty space, it could alter the quantum vacuum around black holes, tweaking the rate at which they evaporate. Think of it as a cosmic thermostat. Dark energy's presence might turn up or down the heat on Hawking radiation, speeding up or slowing down a black hole's eventual demise. Some models even suggest that in a universe dominated by dark energy, black holes could lose mass faster, as if the void itself is helping to dismantle them. Then there's the mind-bending idea that black holes might generate dark energy. One controversial study proposed that the energy trapped inside a black hole's singularity could seep into the surrounding cosmos, acting like a dark energy faucet. If true, it would mean these gravitational monsters aren't just consuming matter, they're fueling the universe's expansion from within. It's a radical notion, like discovering that a drain is secretly also a spring. Of course, testing these ideas isn't easy. Black holes are notoriously secretive, and dark energy's effects are subtle over human timescales. But astronomers are looking for clues in the growth rates of supermassive black holes across cosmic history. If dark energy truly puts the brakes on their expansion, we might find that ancient black holes grew faster than their modern counterparts. Others are simulating black hole mergers in universes with different dark energy strengths, searching for telltale ripples in spacetime that could reveal this hidden relationship. What makes this connection so thrilling is that it ties together the universe's most extreme phenomena, the infinitesimally small quantum world, the crushing gravity of black holes, and the vast, accelerating cosmos. Each discovery in black hole physics could shed light on dark energy, and vice versa. It's a reminder that in the grand puzzle of the universe, even the darkest corners might hold the keys to our biggest questions. What if our universe's oddly perfect dark energy isn't a carefully tuned constant but a cosmic lottery ticket, one lucky draw in an infinite sea of possibilities? This is the spine-tingling premise of the Multiverse Hypothesis, where our reality is just one bubble in a frothing ocean of universes, each with its own unique laws of physics. Picture a vast cosmic casino where the roulette wheel has landed on our number, a dark energy value Goldilocks enough to allow galaxies, stars, and ultimately life to exist. But in other universes, the wheel might have stopped elsewhere, some with so much dark energy that space tears itself apart before atoms can form, others with so little that gravity crushes everything into a hot, dense slurry. The idea gains traction from string theory's landscape of possible vacuum states, a dizzying 10 to the 500 variations of physical constants, each corresponding to a potential universe with different properties. In this view, dark energy isn't fine-tuned, it's random, and we simply find ourselves in a universe where it's survivable. It's like waking up in a lifeboat on an endless ocean. Of course, the boat is sturdy enough to float because you couldn't be conscious to observe it otherwise. This Anthropic Principle offers a neat, if unsettling, explanation for dark energy's improbable value. It's not that the universe was designed for life, but that life inevitably arises only where the numbers align. Critics argue this smacks of surrender, a way to dodge the hard work of finding a deeper physical mechanism. After all, if every possible universe exists somewhere, science loses its predictive power. How do you test a theory that allows for all outcomes? But supporters counter that the multiverse might leave subtle fingerprints. If our universe collided with another bubble in the distant past, the cosmic microwave background could bear scars of that encounter, wrinkles in space-time that next-generation telescopes might one day detect. Others suggest that the statistical distribution of dark energy values across hypothetical universes could still be calculated, offering indirect clues. The real fascination lies in the stakes. If the multiverse is real, dark energy becomes less a mystery than a cosmic accident, one that reshapes our place in the grand scheme. No longer the center of creation, we're just survivors in a reality where the dice happen to roll in our favor. Yet, even as speculation, the idea forces us to grapple with profound questions. Is our universe's apparent fine-tuning a clue to deeper laws, or just a selection effect in an infinite ensemble? And if the latter, what does that say about the nature of reality itself? For now, the multiverse remains a tantalizing thought experiment, a mirror held up to the limits of our knowledge. But in the ever-expanding quest to understand dark energy, sometimes the wildest ideas illuminate the most. What if dark energy isn't a mysterious force at all, but a sign that we've misunderstood gravity itself? This provocative idea turns conventional cosmology on its head, suggesting that Einstein's theory of general relativity, while flawless in our solar system, might need revision when applied to the vast emptiness between galaxies. Imagine gravity as a familiar tune played on a piano, perfectly harmonious in small rooms. But when the hall expands, the notes start to warp, creating echoes we've mistaken for an entirely new instrument. That's the essence of modified gravity theories. Perhaps dark energy is just an illusion, a cosmic mirage born from our incomplete grasp of how gravity operates across the universe. One of the most debated alternatives is modified Newtonian dynamics, or MUND, proposed in the 1980s to explain why galaxies rotate faster than Newton's laws predict. MUND suggests that gravity behaves differently at extremely low accelerations like those found in the outskirts of galaxies. Instead of invoking dark matter to account for the extra gravitational pull, MUND tweaks the equations themselves, as if gravity gains a second wind where the fabric of space grows thin. At first glance, it's an elegant solution, removing the need for invisible substances. But here's the catch. While MUND works remarkably well for individual galaxies, it stumbles when applied to galaxy clusters or the large-scale structure of the cosmos. Worse, it can't easily explain the universe's accelerating expansion, the very phenomenon dark energy was invented to solve. This hasn't stopped physicists from pushing further. Some have developed relativistic versions of MUND, like TVS tensor vector scalar gravity, which attempt to extend the idea into a full-fledged alternative to general relativity. Others explore more radical frameworks like emergent gravity, where gravity isn't a fundamental force but a side effect of deeper quantum processes like the way temperature emerges from the motion of atoms. In these models, what we perceive as dark energy could be a shadow of something far stranger, the hidden thermodynamics of spacetime itself. Yet modified gravity faces fierce challenges. The bullet cluster, a cosmic collision where visible matter and gravitational effects visibly separate, seems to demand some form of invisible mass, undermining pure MUND explanations. And the precise pattern of the cosmic microwave background, that ancient echo of the Big Bang, aligns almost perfectly with predictions based on dark energy, not modified gravity. Still, the allure remains. If gravity does bend the rules on cosmic scales, it would solve two mysteries at once: dark energy and dark matter. No need for unexplained substances, just a new chapter in our understanding of the universe's most familiar force. The debate is far from settled, and that's what makes it so thrilling. Every anomalous galaxy rotation curve, every unexpected gravitational lens could be a clue or a red herring. Whether dark energy is real or just gravity in disguise, one thing's certain: the universe still has secrets to spill, and the moment we think we've got it all figured out, that's when it's most likely to surprise us. Time isn't just a backdrop to the universe, it might be an active player in the dark energy saga. Most theories treat dark energy as a static force, an unchanging push woven into the fabric of space. But what if it's more like a cosmic hourglass, its strength ebbing or flowing as the universe ages? This isn't just a tweak to the equations, it's a revolution in how we understand the relationship between time and the cosmos. Picture a universe where dark energy isn't a fixed setting but a dial turning imperceptibly over billions of years, subtly altering the fate of everything. The idea gains traction from observations that dark energy's density appears eerily balanced with matter now, a coincidence so unlikely it begs for an explanation. If dark energy's strength is tied to time itself, that balance might not be accidental. Think of it like a river carving a canyon. The water's force changes as the landscape evolves, but the two remain locked in a slow, dynamic dance. Similarly, if dark energy weakens as the universe expands, its current match with matter's density could reflect a natural equilibrium, not a cosmic fluke. Some models even suggest dark energy could have been stronger in the early universe, fueling inflation's explosive growth before fading into the background, a hidden conductor orchestrating multiple acts of cosmic history. This raises a profound question. Is time itself shaping the universe's expansion, or is expansion shaping our experience of time? In general relativity, time and space are intertwined, but dark energy's potential evolution introduces a new layer of complexity. Imagine a clock whose ticks aren't regular but stretch or compress with the universe's acceleration. If dark energy changes over time, it could warp our perception of causality on cosmic scales, blurring the line between cause and effect. Philosophers have long debated whether time is fundamental or emergent. Now, physics might be weighing in with clues written in the universe's accelerating expansion. The implications ripple outward. If dark energy evolves, the universe's future could be stranger than we've dared to predict. A weakening dark energy might one day let gravity regain dominance, pulling everything back in a big crunch. Or if it strengthens, it could trigger a big rip, tearing space-time apart at the seams. But here's the twist. If dark energy's behavior is linked to time, these scenarios aren't just endpoints, they're phases in an ever-changing cosmic story. Testing this idea isn't easy, but astronomers have a plan. By measuring dark energy's apparent strength at different epochs using ancient supernova, galaxy clusters, and quasars as cosmic time capsules, we might catch it in the act of changing. Projects like the Dark Energy Spectroscopic Instrument are mapping the universe's expansion history with unprecedented precision, hunting for even the faintest drift in dark energy's influence. A confirmed shift would be more than a discovery. It'd be a paradigm shift, revealing time not as a passive stage but as a director in the universe's unfolding drama. At the intersection of physics and philosophy, dark energy's dance with time challenges our deepest assumptions. Is the arrow of time a consequence of cosmic expansion, or does expansion emerge from time's flow? The answer might lie in the void itself, where the universe's oldest mystery, the nature of nothingness, holds the key to everything. The value of dark energy isn't just a random number, it's a cosmic tightrope walk, a delicate balance between too much and too little. If it were even slightly stronger, the universe would have expanded so rapidly after the Big Bang that galaxies, stars, and planets could never have clumped together. Picture blowing up a balloon with such force that the rubber stretches too thin to hold any shape. On the other hand, if dark energy were weaker, gravity might have pulled everything back into a fiery collapse long before life had a chance to emerge. It's as if the universe's expansion was calibrated with near-perfect precision, landing in a Goldilocks zone where structure and ultimately life could exist. This eerie fine-tuning is where the Anthropic Principle enters the conversation. The idea is deceptively simple. We observe dark energy's value to be just right for our existence because, well, we're here to observe it. In other words, if the numbers had been different, there'd be no one around to wonder why. It's like a puddle marveling at how perfectly its shape fits the hole it's in, not realizing the hole came first. But this explanation raises as many questions as it answers. Is dark energy's value a happy accident, or does it hint at something deeper, a law of nature we haven't yet uncovered? Some scientists argue the Anthropic Principle is a cop-out, a way to sidestep the search for a fundamental explanation. After all, physics thrives on uncovering why things are the way they are, not shrugging and saying, because otherwise we wouldn't be here. But others counter that the principle might be a clue pointing toward a multiverse, a vast ensemble of universes, each with different physical constants. In this scenario, we just happen to live in one where the numbers line up for life, while countless others with inhospitable dark energy values remain barren. It's like flipping a coin an infinite number of times. Eventually, you'll get a sequence where it lands on heads every time, and we're the unlikely observers of that run. Yet, even if the multiverse explains the fine-tuning, it doesn't necessarily satisfy the deeper itch. Why does any universe have dark energy at all? Could there be a physical mechanism, some undiscovered symmetry or dynamic, that naturally leads to the value we see? Some theories suggest dark energy's strength might be tied to the universe's age or size, evolving over time to settle into its current state. Others propose that it's not a fixed property but the residual effect of a much grander process, like the slow decay of an invisible field left over from the Big Bang. The stakes here are philosophical as much as scientific. If dark energy's value is purely random, a roll of the cosmic dice, it challenges our instinct that the universe should make sense in a way we can comprehend. But if there's a deeper reason, its discovery could rewrite the rules of reality. For now, the Anthropic Principle stands as both a tantalizing hint and a frustrating enigma, a reminder that sometimes the universe's most profound mysteries aren't just about how things work, but why they work for us. And that's a question that lingers long after the equations are written. Quantum entanglement, the bizarre phenomenon where particles remain mysteriously linked across any distance, instantly mirroring each other's states, might hold clues to dark energy's deepest secrets. Picture two electrons born from the same quantum event, separated by billions of light years. Change the spin of one, and the other instantly responds, as if space and time don't apply to their connection. Now imagine this spooky action not just between particles, but woven into the fabric of the vacuum itself. Some theorists suggest that entangled vacuum fluctuations, those fleeting particle-antiparticle pairs popping in and out of existence, could collectively generate a repulsive force, one that stretches space-time and accelerates the universe's expansion. It's a radical idea, dark energy as the cosmic echo of quantum entanglement on a universal scale. But how could something so small-scale influence the entire cosmos? Think of entanglement not as isolated threads, but as a vast, invisible web. If countless quantum fluctuations are entangled across the universe, their combined behavior might create a subtle but pervasive energy field. This isn't just empty speculation. Certain models in quantum field theory show that entangled systems can exhibit non-local effects, where the whole becomes greater than the sum of its parts. Apply that to the vacuum and you get a tantalizing possibility. What if dark energy emerges from the universe's quantum conversations, a kind of background hum from particles whispering to each other across the void? Critics, of course, raise eyebrows. Entanglement is delicate, easily shattered by interactions with the environment. Scaling it up to cosmic proportions seems like trying to build a skyscraper out of soap bubbles. Plus, there's no direct evidence yet that entangled vacuum fluctuations could produce dark energy's smooth, uniform push. But supporters counter that the universe's sheer size might stabilize these effects, averaging out quantum weirdness into a force we perceive as dark energy. It's like the difference between a single water molecule and an ocean wave. One is chaotic, the other a predictable surge. The real intrigue lies in the implications. If entanglement fuels dark energy, it would mean the universe isn't just expanding, it's remembering itself, with every particle state subtly influencing the whole. This could even reshape our view of cosmic horizons. Normally, entangled particles lose their connection when one crosses a black hole's event horizon. But if entanglement is fundamental to dark energy, does that mean black holes somehow filter the vacuum's energy, altering expansion locally? Wild as it sounds, studying entanglement in extreme environments like near black holes or in the early universe might reveal hidden links to cosmic acceleration. For now, these ideas linger at the edge of theory, waiting for experiments to catch up. Next-generation quantum simulators could mimic entangled vacuum states in the lab, while telescopes might one day detect anomalies in cosmic expansion tied to quantum correlations. Whether entanglement truly plays a role in dark energy or not, the mere possibility is exhilarating, a reminder that the universe's greatest mysteries often bridge the smallest and largest scales. And in that uncharted territory between quantum mechanics and cosmology, the next revolution in physics might already be entangled, waiting to be uncovered. The early universe was a cauldron of extremes, a searing, dense soup of particles where gravity ruled unchallenged. In those first fiery moments after the Big Bang, dark energy, if it existed at all, would have been drowned out by the sheer intensity of matter and radiation. Picture a crowded room where one quiet voice goes unheard. Dark energy's subtle push would have been negligible against the roaring chaos of the primordial cosmos. Yet somehow, over billions of years, this whisper grew into a shout, overtaking gravity to become the dominant force shaping the universe's fate. How did this reversal happen? The answer might rewrite our understanding of dark energy's true nature. One compelling idea is that dark energy's strength isn't fixed but tied to the universe's expansion. In the beginning, when matter was packed tightly, its gravitational pull kept dark energy in check, like a heavy blanket smothering a spark. But as space stretched and matter diluted, the balance shifted. The energy of the vacuum, once overshadowed, began to assert itself, its repulsive force growing more pronounced as the cosmos thinned out. This isn't just speculation, it's etched into the equations of general relativity. Einstein's cosmological constant, if real, would have remained constant, but its relative influence would have surged as matter's density faded. It's like a seesaw where one side gradually loses weight, letting the other side descend. But what if dark energy wasn't always there? Some theories propose it emerged later, a byproduct of space-time's evolving structure. Imagine the early universe as a frozen lake. As it expands, cracks form in the ice, releasing trapped energy. Similarly, as space-time stretched, new degrees of freedom might have unlocked, giving rise to dark energy as a sort of cosmic thaw. Other models suggest dark energy could be the remnant of an ancient phase transition, a moment when the universe's underlying symmetries shifted, leaving behind a latent energy that now drives acceleration. These scenarios paint dark energy not as a fundamental constant, but as a dynamic consequence, like the wake left behind by a passing ship. The stakes here are enormous. If dark energy was negligible in the early universe, it strengthens the case for vacuum energy, a force intrinsic to space itself, waiting for matter to dilute before taking center stage. But if it emerged later, it could point toward something far stranger, a universe where the laws of physics aren't static but evolve over time. Clues might lie in the cosmic microwave background, that fossilized light from the universe's infancy. Subtle irregularities in its patterns could reveal whether dark energy was already subtly at work, or if its influence ignited like a slow burning fuse. Either way, the early universe holds the key. By peering back to a time when dark energy was just a shadow, we might finally glimpse what it truly is: a fundamental thread woven into reality, or a cosmic accident, a ripple in the fabric of space-time that grew into a wave. And that distinction doesn't just change the story of our past, it reshapes the destiny of everything. What if everything we see, every galaxy, every star, even the space between them, isn't truly three-dimensional but a cosmic illusion? The holographic principle dares to suggest exactly that, proposing our universe might be a vast, shimmering projection, its true essence encoded on a distant two-dimensional surface. Imagine the cosmos as a movie screen, with the stars and planets mere shadows cast by deeper, hidden data. This isn't just a sci-fi fantasy. It's a serious theoretical framework born from the study of black holes, where the information swallowed by their immense gravity appears to be stored on their surface, not lost within. Now, physicists are asking an even wilder question. Could dark energy, that mysterious force stretching the universe apart, be a side effect of this holographic nature? Think of it like a computer struggling to render an ultra-high-resolution game. The more the universe expands, the more pixels of space-time it needs to generate, stretching its computational resources thin. Dark energy, in this view, might be the cosmic lag, a subtle resistance emerging as the holographic universe strains to maintain the illusion of depth. It's as if the fabric of reality itself has a hidden tax, a toll paid in acceleration every time space grows. Some models even suggest that the energy of the vacuum, which quantum mechanics says should be enormous but observations show is faint, could be naturally diluted by this holographic encoding, resolving the infamous vacuum catastrophe at a stroke. But the implications go deeper. If the universe is truly a hologram, then dark energy might not be a force at all, but an artifact, a glitch in the cosmic code. Just as a shadow can distort depending on the angle of light, the acceleration we observe could be a misinterpretation of how information is projected from the universe's true 2D boundary. This would mean our entire understanding of cosmic expansion is like trying to explain a movie's plot by studying only the flickers on the screen, oblivious to the projector behind it. Critics, of course, point out the lack of direct evidence. The holographic principle remains a dazzling mathematical construct, with no experiment yet able to confirm whether our universe is truly a lower dimensional reality in disguise. But supporters argue that its elegance is undeniable. By unifying black hole physics, quantum mechanics, and gravity under a single framework, it offers a path to explaining not just dark energy, but the very nature of space-time itself. Future experiments, like precise measurements of quantum entanglement or the cosmic microwave background's fine scale patterns, might one day reveal holographic fingerprints, subtle anomalies that betray the universe's true, flattened nature. For now, the holographic principle stands as one of the boldest ideas in physics, a reminder that reality might be far stranger than it appears. And if it's right, dark energy could be more than a mysterious force. It might be the universe's way of telling us we've been reading the map all wrong, mistaking the projection for the source. The answer, if it exists, is written not in the stars, but in the hidden dimensions where the cosmos keeps its deepest secrets. Could the act of observing the universe actually shape its expansion? It's a question that blurs the line between physics and philosophy, where some radical theories suggest dark energy and consciousness might be bizarrely intertwined. Picture this: if the universe accelerates not just because of invisible energy, but because sentient beings are watching it, that would turn cosmology on its head. The idea borrows from quantum mechanics, where particles behave differently when measured, as if reality itself responds to observation. Now stretch that concept to cosmic scales. What if the universe's expansion is somehow aware? It's dark energy nudged by the collective gaze of galaxies, stars, and even us. This isn't just wild speculation, it's rooted in the participatory universe hypothesis, a fringe but fascinating offshoot of quantum theory. Proponents argue that consciousness isn't a passive bystander but an active participant in shaping reality. Apply that to dark energy and you get a mind-bending implication. The more the universe is observed, the more it might choose to accelerate, as if existence itself thrives on attention. It's like the old thought experiment about a tree falling in an empty forest, except here, the forest is space-time, and the sound is the universe deciding how fast to stretch. Of course, mainstream science dismisses this as metaphysical fantasy. There's zero empirical evidence that human or any consciousness affects cosmic expansion. Dark energy's uniformity across billions of light years suggests it's a fundamental force, not a psychological quirk. Critics point out that if observation influenced dark energy, we'd expect weird fluctuations in expansion rates near densely populated galaxies, which we've never seen. And yet, the idea persists, less as a testable theory than a provocative metaphor, one that underscores how deeply dark energy challenges our notions of reality. What makes this concept so enduring isn't its scientific rigor, but its sheer audacity. It forces us to confront the limits of objectivity. Can we ever truly separate the observer from the observed? Even if consciousness doesn't literally drive dark energy, the question lingers: why does the universe seem so finely tuned for life? Whether coincidence, multiverse luck, or something stranger, dark energy's mysteries remind us that the cosmos might still have surprises hiding in the shadows. And sometimes the wildest ideas are the ones that stretch our imagination farthest, like the universe itself. The search for dark energy's true nature is pushing physicists into uncharted territory, where the very foundations of reality might need reimagining. One audacious idea gaining traction is that space-time itself isn't fundamental, but emerges from deeper, more exotic processes, like how temperature arises from the chaotic motion of atoms. In this view, dark energy could be a side effect of spacetime's granular structure, a sort of cosmic friction generated as the universe's underlying pixels interact. Picture a vast digital screen. From a distance, the image looks smooth, but zoom in close enough, and you'll see the individual pixels, and maybe even glitches in how they render. If spacetime has a similar hidden architecture, dark energy might be the subtle artifact of its code. Then there's the radical notion that the speed of light isn't constant but varies over cosmic time or distance. While Einstein's relativity hinges on light's unwavering speed, Some theorists suggest that tweaking this assumption could eliminate the need for dark energy altogether. Imagine light slowing down imperceptibly over billions of years, making distant supernovae appear fainter, and thus farther away than they truly are. What we've interpreted as cosmic acceleration might instead be a grand optical illusion, a misinterpretation of light's fading stamina. It's a long shot, but if proven, it would upend centuries of physics, trading dark energy for a rewritten cosmic rulebook. Meanwhile, other researchers are probing whether dark energy could arise from the universe's topology, its hidden shape. If space has subtle folds or extra dimensions curled into microscopic loops, their geometry might generate repulsive forces we perceive as dark energy. Think of it like a cardboard tube, flat from a distance, but run your finger along it and you feel the curve. If the cosmos has similar hidden contours, they could be invisibly stretching the fabric of reality. The most exhilarating possibility, dark energy might not be one thing but many, a cocktail of exotic phenomena, each contributing a piece to the puzzle. Perhaps vacuum energy, evolving fields, and emergent gravity all play a role like instruments in a cosmic orchestra. Future experiments, from quantum simulators to space-based gravitational wave detectors, could finally tease these threads apart. Whether the answer lies in revised gravity, new dimensions, or something entirely unforeseen, one thing's certain: the universe still holds cards it hasn't shown us. And when they're finally played, the game of cosmology will never be the same. Dark energy isn't some mystical force lurking in the shadows of the cosmos. It's a real, measurable phenomenon with concrete effects on the universe. Yet, it's often misunderstood, tangled up with other scientific concepts, or even sensationalized as something out of a fantasy novel. One of the biggest mix-ups. Dark energy versus dark matter. While both are invisible and mysterious, they couldn't be more different. Dark matter acts like cosmic glue, its gravity holding galaxies together, while dark energy does the opposite. It's the repulsive force pushing space apart. Imagine dark matter as the scaffolding of the universe, silently shaping its structure, while dark energy is the unseen hand stretching that scaffolding wider every second. Then there's the myth that dark energy is some form of anti-gravity. It's an easy leap to make. After all, gravity pulls and dark energy seems to push. But here's the twist: dark energy isn't fighting gravity in the way you might think. Instead of reversing gravity's pull, it's more like an inherent property of space itself, a kind of tension woven into the fabric of reality. Think of it like a rubber sheet that naturally expands on its own, no matter what's placed on it. Gravity might bend that sheet, but dark energy keeps stretching it relentlessly and uniformly. Perhaps the most persistent misconception is that dark energy is something supernatural, a cosmic ghost or an unexplained anomaly. In reality, it's as much a part of physics as electricity or magnetism, even if we don't yet fully understand it. Scientists aren't just guessing, they've measured its effects through supernova, galaxy surveys, and the cosmic microwave background. It's not magic, it's math, observation, and evidence. The mystery isn't whether dark energy exists, but why it behaves the way it does. Clearing up these myths isn't just about setting the record straight. It's about appreciating dark energy for what it truly is, one of the greatest puzzles in modern science. The more accurately we understand it, the closer we get to unlocking the universe's deepest secrets, and that's a journey worth taking without the fog of misunderstanding clouding the way. Hollywood loves a good cosmic mystery, and dark energy has become the ultimate MacGuffin, an invisible force rewritten as everything from a superweapon to a portal to alternate dimensions. Take Marvel's Doctor Strange, where dark energy is reimagined as the source of sorcery, a glowing, crackling power that bends reality to the will of its wielders. Or consider video games like Mass Effect, where it fuels faster than light travel, hand-waved as Element Zero, that conveniently ignores the actual physics of cosmic expansion. These portrayals are thrilling, no doubt, but they're about as scientifically accurate as a lightsaber duel in the vacuum of space. Then there's the trope of dark energy as a looming apocalypse. In films like Knowing or The Cloverfield Paradox, it's often a ticking time bomb set to rip apart planets or unravel the fabric of existence. The irony. Real dark energy works in slow motion. Its effects unfold over billions of years, not in a single explosive climax. It's less a Hollywood disaster and more like the gradual fading of an old photograph, where the edges blur and the colors dim almost imperceptibly. Books and TV aren't much better. Sci-fi novels sometimes treat dark energy as a sentient entity, a conscious force with motives and whims. The truth is far stranger. Dark energy doesn't do anything. It doesn't scheme, it doesn't evolve, it just is, a relentless, impersonal push woven into the universe's DNA. Even acclaimed works like Interstellar sidestep the real science, opting for wormholes and time dilation while leaving dark energy on the cutting room floor. But here's the twist: these creative liberties aren't failures. They're proof of how deeply dark energy captivates us. When science can't yet explain something, art rushes in to fill the void, sometimes with lasers and explosions, other times with existential dread. The real magic lies in the gap between fiction and reality, where the unanswered questions spark our imagination. Dark energy may not power superheroes or doom civilizations, but its true story, a mystery hiding in plain sight, rewriting the fate of everything, is stranger than any script. And that's a plot worth sticking around for. Every time humanity turns its gaze toward the cosmos, we face the same profound question. How much should we invest in understanding the universe when so many urgent challenges, climate change, poverty, disease, demand our attention and resources right here on Earth? The study of dark energy isn't cheap. It requires billion-dollar telescopes, international collaborations spanning decades, and the brightest minds diverted from other pressing fields. Skeptics argue that these resources could be better spent solving immediate, tangible problems. After all, what practical difference does it make if the universe expands forever or collapses in a distant future none of us will live to see? But here's the counterpoint: the pursuit of knowledge has never been just about practicality. When Galileo pointed his telescope at Jupiter's moons, he wasn't solving hunger or curing plagues. When Marie Curie studied radioactivity, she wasn't thinking about economic inequality. Yet these discoveries reshaped our world in ways no one could have predicted. Understanding dark energy isn't just about mapping the universe's fate, it's about probing the fundamental laws of reality. Laws that might one day unlock technologies or insights we can't yet imagine. The microchip, the laser, even the internet, all emerged from fundamental research once considered abstract or impractical. Who's to say dark energy won't be the next catalyst for revolution? There's also the deeper, more philosophical argument. Exploration is woven into human DNA. We climb mountains, dive into oceans, and send probes to the edge of the solar system, not because it's profitable, but because we're driven to understand our place in the cosmos. Dark energy is the ultimate frontier, a mystery that forces us to confront the very nature of existence. If we abandon curiosity in the name of pragmatism, we risk losing something essential: the awe and wonder that remind us why we strive to survive and thrive in the first place. That said, the ethical balance is delicate. No one suggests ignoring Earth's crises to fund space telescopes. but history shows that scientific progress isn't a zero-sum game. The same institutions studying dark energy also pioneer technologies with earthbound applications, advanced computing, precision engineering, even medical imaging. The challenge isn't choosing between the stars and the soil beneath our feet, but recognizing that the two are intertwined. The universe's greatest mysteries often illuminate our own world in unexpected ways. And sometimes the act of looking up is what teaches us how to better look after one another. Imagine scrolling through images of distant galaxies on your laptop, sipping coffee, when suddenly you spot something odd. A smudge of light where none should be, or a strange distortion in a star cluster. That aha moment isn't reserved for astronomers in white lab coats. Thanks to citizen science projects, anyone with curiosity and an internet connection can help decode dark energy's riddles. Platforms like Zooniverse's Galaxy Zoo or the Dark Energy Explorers initiative turn cosmic data into a global puzzle, inviting ordinary people to classify galaxies, track supernova, or flag anomalies that algorithms might miss. It's a revolution in discovery, the universe's biggest mystery cracked by millions of tiny contributions. Take the Einstein at Home project, which harnesses idle computing power from volunteers' devices to sift through gravitational wave data. While users sleep, their laptops become virtual telescopes, passing signals that could reveal how dark energy warps space-time. Or consider CosmoQuest, where participants map craters on celestial bodies, indirectly refining models of cosmic expansion. These projects aren't just busy work, they've led to real breakthroughs. In 2017, a Dutch schoolteacher poring over Galaxy Zoo images discovered a rare green pea galaxy, a type crucial for understanding early universe conditions. Who's to say the next critical clue won't come from a retiree in Tokyo or a teenager in Buenos Aires? The beauty of this approach lies in its humility. For decades, science operated like a cathedral, elite architects designing theories while the public admired from afar. Now, it's more like a bustling bazaar where everyone brings something to the table. Crowdsourcing doesn't just accelerate research, it diversifies it. An artist might notice a pattern a physicist overlooks. A gamer's knack for spatial reasoning could outmatch a supercomputer's algorithms. Even failure is valuable. When thousands of independent observers agree on a classification, it sharpens the data's reliability, like a cosmic version of wisdom of the crowd. But the impact goes deeper than data points. By inviting the public into the process, these projects demystify science, replacing jargon with tangible participation. A parent explaining galaxy shapes to their child isn't just teaching, they're perpetuating a cycle of curiosity. Schools use these platforms to turn abstract physics into hands-on lessons, proving that dark energy isn't some distant abstraction, but a living, breathing enigma we're all piecing together. Of course, skeptics argue that amateurs can't replace trained scientists. They're right, but that's not the point. Citizen science isn't about swapping expertise for enthusiasm. It's about amplifying both. Researchers get eyes and brains they'd never have access to otherwise, while participants gain a stake in humanity's grandest quest. It's a symbiotic relationship where the act of observing the universe changes how we see ourselves within it. And in that shared journey, dark energy stops being a puzzle for them and becomes a story for us, one we're writing together, one galaxy at a time.